Okay, here we will talk about the given sortation to do a QR decomposition of a matrix. Remember that the QR decomposition of a matrix is when you represent it as a product of two matrices Q and R, where Q is orthogonal and R is an upper triangle matrix. Okay, so it has zeros below the diagonal. Okay. And so you can use a given sortation to do the QR factorization. The goal will be to apply several given sortation to the matrix to get our upper triangle matrix R. And then basically all these given sortation applied will be equal to Q transpose. Because remember, Q is orthogonal, so its inverse is its transpose. Remember? And so if you multiply by Q transpose on the left, get that Q transpose A is equal to Q transpose Q times R, but Q transpose Q is the identity matrix, so we just get R. Okay. So now, what is a given sortation? So as it says, it's a rotation basically. So let's say you are in 3 dimensions, but you can do that in how many dimensions you want. Let's say I have a given vector. Okay. So let's say that this is the z-axis, the y-axis, and the x-axis. Basically, what it does is here for the moment our vector it has we suppose it has 3 non-zero components. Okay, as I said, we can do that in whatever dimension that we want. Okay, the goal will be to rotate this vector. Let's say that we will first rotate it around the z-axis, so we can put the new vector in the xz plane. Okay. And so our new vector its y component will become 0, okay? And then we can do a second rotation now around the y-axis, here in this case, and so we get the new vector which has only a non-zero x component. Okay? So first we eliminated the y component and then we eliminate the z component, okay? And as I said, here we are in 3 dimensions. You can do that in as many dimensions as you want. If you have a vector with 4 dimensions, you can first apply it 1 rotation to eliminate the second component. Then second rotation and the third one. So every time you will eliminate 1 element. And then so finally you will get a vector which has only a non-zero component in the first row. Okay, the non-zero component, it's a bit tricky. It can be 0. Okay, the non-zero components, they can be 0, but it's not necessarily the case. Okay, we want the other elements to become 0, but if for whatever reason one of the non-zero components is also 0, doesn't matter. Okay, but they don't have to be 0. Okay, the other elements have to become 0. Okay. Okay. And so basically you can use that to do a QR factorization of a matrix. As I said, if let's say again that you are in 3 dimensions, we will apply let's say that you are so we have a 3 by 3 matrix. So it has, let's say it has 3 vectors, and yeah, we are in 3 dimensions. Let's maybe name these elements A11, A21, A31, A32, A33, A22, A21. Sorry. It's A12, A13. Not here, that's correct. A22. A23. Okay. So first we will consider the first column vector of A, and we will eliminate this element by applying a first given rotation. Then we will eliminate the second one, a free one, so the first component of the vector. And then we will go to the second column vector and eliminate the last element, because remember we want an upward triangular matrix. Okay, that's our goal. And so if we apply all these rotations, we will get our upward triangular matrix. And all this given rotation will be equal to Q transpose. Okay. So now, how do we proceed? Well, our given rotation, which we generally we call it J, but you can call it whatever you want. Basically, it has ones in the diagonal. So it how can I say that? In your matrix, you will have ones, cosine, 2 cosines, 1 sine, and a negative sign. Okay. And for cosine, we generally write just the letter C to make it simpler, and for sine, we write S. Okay. Just to keep it simple. And you will have, of course, also lots of zeros. Basically, the element that you want to eliminate, at the place of the element, you will always place the negative sign. Okay. So let's say we want to eliminate A21. We will put a negative sign in the second row, first column. Okay. And to eliminate A21, which is the y component of the first vector, as I said by my example before, we can rotate here around the z-axis to first get rid of the y component. And so to show that you rotate around an axis, you will put a 1 here in the z component, and the ones are always put in the diagonal. Okay. So here we rotate around the z-axis, so there will be a 1 in the z component. Okay, and the ones are always put in the diagonal, and yeah. Okay. And then you will put the others, the sine and the 2 cosines, in such a way that they always have to form a square, and the 2 cosines, they are always they also always form a diagonal, and the sine and the negative sign also. Okay. I hope you understand what I say. The 2 cosines, the sine and the negative sign, they always form like a square, basically. And the two cosines they form a diagonal, and the sign and the negative sign also. Okay. So here we rotate around the z-axis, but if you are in 3 dimensions, you can, for example, also rotate around the y-axis. In this case, you put a 1 in the y component, and remember the ones are only on the diagonal. Okay. And also you put 0 next to that 1, basically the same row and the same column of this one of the dimensions around which of the dimensions around which you are rotating. There will be zeros there. Okay, so here we rotate around the z-axis. So in the column and the row where this one is, there will only be zeros. At where there isn't the one. Okay, I hope it's clear. So here we are in 3 dimensions and we rotate around the y-axis. So in the second column and second row there will be zeros, except where there is the one. Okay, for example, this, if we rotate around the y-axis, it's when we want here to eliminate the element A31. This would be our second rotation here in orange. Okay, so we eliminate the z component here, and so we put the minus sign in the same place. So we put it in the third row and first column where our element A31 is. I hope this is clear. And remember, the two cosines, the sine and the negative sign, have to form a square. And the negative sign and sine are they form a diagonal, and the two cosines, they also form a diagonal. Okay. Okay. We could also rotate around the x-axis. In this case, we will put a 1 in the x component, and remember again, the ones are always in the diagonal. Okay, and so here we will put zeros in the same column and the same row. Okay, and also the square that is formed by the two cosines, the sine and the negative sign. The negative sign will always be on the bottom left corner of. So here we have only 4 cases left. So our cosines and sines will be here. The negative sign will always be on the bottom left corner. The sign on the top right, because they form a diagonal. Then you put the two cosines in the place that are left. Okay. Okay. And now, if you are in higher dimensions, you won't rotate only around one axis, but around several. Okay. Because your rotation is a plane, so it has 2 dimensions. If you are in 3 dimensions, there will be only 1 dimension left, because you use 2 dimensions to rotate. But in higher dimensions, there will be more than 1 axis left, and so you will rotate around more than 1 axis, and so you will have more than one in the diagonal. Okay, so for example, if we're in 4 dimensions, we can put 2 ones in the first and second dimensions, and again there will be zeros in the same row and same column. Okay, and then here, so we have a square here. and the negative sign is on the bottom left. Okay, so this will be our matrix. For example, also we can do the following. Here there will be zeros again, because the same rows and same column of the ones, they have to contain only the 1 and then the zeros again, so the square will be here. Yeah. That will be the following. Also, what could happen is the following. For example, you have a 1 here, so you rotate around the first axis, but then you rotate also around the third axis. In this case, you have 4 elements left again, so the square will be here. Okay, and so the negative sign will be at the bottom left. It will form a diagonal with the other sign. Okay, so remember. Then you have the 2 cosines. Okay, which also form a diagonal. Okay, and so you can extend that to how many dimensions you want. There will always be a 1 in the diagonal in the row of the axis around which you are rotating, and yeah, the cosine and sines, they form a square, and the negative sign is in the place of the element you want to eliminate. And so the formula, let's again look at our 3x3 matrix. Basically, so let's say we want to eliminate A21. So our given rotation will be, remember the minus sign is at the same place. Here we can remember the minus sign is always at the bottom left. So basically the 2 cosines will be here and the sign here. Okay. Also remember that the negative sign and the sign have to be in the diagonal. Okay. So your sign is necessarily here. Okay. And so they form a square. And also you are rotating around the z-axis. Okay. So there will be 0, z. Now our cosine is given by the top element of the vector, so here a11, over the square root of this element squared, plus the element you want to eliminate, so a21 squared. Okay. Okay, and the sign is given by the element you want to eliminate over the square root of this element squared and the top element. Okay, so basically it's the inverse. Also, very important, remember that cosine and sine, we often say cosine of an angle, or sine of an angle. Let's say cosine of phi, or sine of theta. But to do a QRT composition with the given rotation, we almost never need an angle. Okay, so yeah, we just need these formulas here. Okay, this formula comes from the fact that basically the square root of this, the sum of these two elements square, that can be seen as the hypotenuse. Okay, and remember, cosine is adjacent over the hypotenuse. So here, for example, our element A11 will be the adjacent if our angle would be here. Let's call it theta. And remember, sine is the opposite over the hypotenuse. So in our case, A21 will be the opposite. Okay. And basically, how can you do that? To do the rotation, remember, you only consider two dimensions, okay? And these two dimensions, they can form a triangle, and so you can use that, okay? For example, if you rotate in the xy plane, as we did in our first rotation, remember when we rotate around the z-axis? So we rotate around the xy plane. We rotate the xy plane, basically. The plane rotate. We can imagine if we have our vector here, that the x and the y component, they form a triangle, basically, if we don't consider the z component. And so basically you can let's maybe draw it this way. So you can do trigonometry. Here there will be the angle, here will be the opposite, that will be the adjacent. Okay, so remember, when you rotate, you consider the plane that you rotate. So you consider two dimensions to rotate around the axis of the other dimensions, and these two dimensions, so they form a plane, and so you can imagine that the components that are in these dimensions, the components of this vector that are in these dimensions, they form a triangle, okay? And so you can use basic trigonometry, and that's where these formulas here come from. Cosine will be the adjacent over the hypotenuse, and sine the opposite over the hypotenuse, right? And so once you have found your cosine and sine, you put them in your matrix, you apply it to A. So let's say we do our first given rotation, then you will get, let's call it A1, a matrix where the second element, let's say again that we're in 3 dimensions, the second component of first vector will be 0. Okay. And now we could consider the third component of the first vector. And so remember, cosine will be the top element over the square root of the top element squared plus the element we want to eliminate. So this will be a11 over the square root of 1 squared plus a31 squared, okay? And sine will be the element we want to eliminate over the square root of this element squared plus the top element. Now, I want to point out just that if you do a QR factorization, remember our R has zeros below the diagonal, okay? So once we are finished with our first vector, let's say that we have only one non-zero element left in the first vector. Our goal isn't to eliminate all except one component of the second vector, okay? Because we want an upper triangle matrix, okay? And so here, if you're in 3 dimensions, the the second vector has only 1 0, because if you are in 3 dimensions, okay? And so basically what you do is you will consider the submatrix, okay? If you begin with an n by n matrix, you, for the second vector of this n by n matrix, you will consider basically the n minus 1 times n minus 1 matrix, okay? So here, first we had a 3 by 3 matrix. Now, to find our new second vector, we consider the 3 minus 1 times 3 minus 1 matrix, or 2 by 2 submatrix basically. And so the top element of this vector here, the second vector, the first vector of the submatrix basically, the top element will be the element in the submatrix, okay? Not the top element of our original vector, okay? And so, sorry, if we had again our elements, so let's say we have A11, let's call it prime because we apply the rotations, A12, A. Okay, and that now we consider the submatrix here. So remember our given rotation here. Let's call it J prime maybe, just to illustrate it. Basically, you will only consider the dimensions of the submatrix. So our submatrix here is a 2 by 2, and so our given rotation will be in 2 dimensions. And so remember, we want to eliminate A32 in this case, so we will put a negative sign here, a sign here, a cosine here, and a cosine here. Now, we want to apply it to A, but J hasn't the same number of columns as A has rows. So basically, we will find, we will input our given rotation, and then we will put a 1 in the diagonal and 0 elsewhere, so that we have the same number of dimensions, okay? And again we put the given rotation in the bottom right, because otherwise the minus sign wouldn't be in the same place as the element of in the matrix A that we want to eliminate, okay? Okay, so what you could do in another way is you do only one given rotation, and you find the place where your minus sign, sine, and cosines are, okay, and then you look how you can have the same number of columns as A has of rows, and so you will put 1s in the diagonal until you get the same number of columns as A has rows, and 0 in the same row and columns of this as this one. Okay. I hope this helps you. And so you can extend that to how many dimensions you want. Okay. So as I said, if you have, for example, 5 by 5 matrix, 4, 5, 2, 3, 4, 5. Okay. You will apply 4 rotation to eliminate all elements except one of the first vector. Then you will consider the submatrix, the first submatrix. And so here, for the second vector, you will apply 3 rotations, because remember you want an upper triangle matrix. Then you will consider the submatrix. Okay. Here you will apply 2 rotations. Then you will consider the submatrix, and here you will apply 1 rotation. Okay. And so you can extend that to an n by n matrix. If it's an n by n matrix. If it has n let's say that this is our n by n matrix. If it has n rows, for the first vector you will apply n minus 1 rotations. Okay, because remember you want only one of the first component. You only want that the first component of the first vector is non-zero. Again, it doesn't necessarily have to be non-zero, but we don't need that it's also 0. Okay, and then you will consider the n minus 1 times n minus 1 submatrix. And here we will apply n minus 2 rotations. Okay, and then you continue, and once you have applied all your rotations to A, you get your upper triangle matrix. And all these rotations, the product of these rotations, will be equal to Q transpose. And so you can find that Q will be equal to J1 transpose, J2 transpose, all the way to Jn transpose. Okay. So I hope it's clear. So remember that when you use Gibbons rotations, okay, your Gibbons rotation is in the form that the axis around which you are rotating, you will put a 1 in the diagonal of the dimensions which this axis represents, then 0 elsewhere. Okay, and you will put 2 cosines, a sine and a negative sign. They have to form a square. The negative sign is always on the bottom left of the square, and it is in the same place as the element you want to eliminate in your original matrix. And it has to form, it is in diagonal with the other sign, and the cosine, and the sine, they also, the 2 cosines, they also form a diagonal. Okay, and the formulas are given by cosine is equal to the top element of the vector, in the submatrix, if you consider a submatrix, over this top element squared plus the element you want to eliminate. And sine is the opposite. It's the element you want to eliminate over the square root of this element squared plus the top element. And so remember, they form a triangle in the plane that you are rotating. Okay. So for example, if you rotate around the z-axis, so this will be your x and here y component. And so this is, yeah, it's trigonometry. And so you apply your Gibbons rotation and you can get your upper triangle matrix R and your orthogonal matrix Q. Okay. Yeah. So I hope you understand it. Yeah. Thanks for watching.